What if the universe isn't as full as it seems? What if, instead of being surrounded by a balanced spread of galaxies and matter, we're drifting inside a massive cosmic void, a place so vast and so empty that it spans nearly 2 billion light-years? This is the enigma of the KBC Void, a mysterious underdense region uncovered by astronomers Keenan, Barger, and Cowie. Far from being just an empty spot in the cosmos, this void could be skewing our observations of the universe's expansion, possibly challenging the very existence of dark energy. In this video, we dive into one of the largest and most puzzling structures ever discovered in space, and explore how this vast emptiness could change everything we know about the universe. Named after the three astrophysicists who identified it, Keenan, Barger, and Cowie, the KBC Void is among the most colossal, underdense regions of space we've ever discovered. Imagine a region so vast, so unfathomably enormous, that our entire Milky Way galaxy is just a minuscule dot within it. And yet, unlike the sea of galactic clusters that make up the large-scale structure of the cosmos, this void contains significantly fewer galaxies than the rest of the universe. It's like standing in the middle of a silent desert when you know you should be surrounded by a bustling city. But why does such a void exist? What are its implications? Could this vast emptiness explain the inconsistencies we see in the measurements of the universe's expansion rate, an issue that has haunted cosmologists for decades? Could it even imply that we are in a privileged location in the cosmos, an idea long dismissed as unlikely due to the Copernican principle? And if the KBC Void is real and we're inside it, then what does that mean for everything we know about the cosmos? To understand the KBC Void, we first need to dive deep into the structure of the universe itself. On the grandest scales, the universe is not a uniform sea of stars and galaxies. It is a cosmic web, a vast network of filaments, nodes, and voids. Imagine a 3D spiderweb stretching across billions of light-years, where the threads are made of dark matter and galaxies alike, clustered together like dewdrops on the strands. These threads intersect at nodes, massive galactic superclusters, while in between them lie immense voids, areas with relatively few galaxies, stars, or matter of any kind. These voids are not unusual. In fact, they're a natural part of the universe's large-scale structure. But the KBC Void isn't just another cosmic void. It's something much larger, more mysterious, and more significant. The KBC Void was proposed in 2013, but its implications echo through decades of cosmological research. What makes it so important is not just its size, although it is gargantuan, but its potential to reconcile a persistent problem in cosmology, the Hubble tension. This refers to the discrepancy in measurements of the Hubble constant, the value that determines how fast the universe is expanding. Depending on whether you measure it by looking at the early universe through cosmic microwave background data from missions like Planck, or from the local universe, using supernovae and Cepheid variables, you get different numbers. This mismatch isn't trivial. It threatens to undermine the very foundations of the standard cosmological model. Enter the KBC Void. If we really are living inside a massive underdense region, it would cause local expansion rates to appear faster than the global average. That's because gravity works more weakly in underdense regions. Less matter means less pull, and thus galaxies in and around the void appear to be speeding away faster than they would in a denser region. It's like the fabric of space-time is stretching more rapidly here than elsewhere. If true, this could explain why our local measurements of the Hubble constant are higher than those derived from the early universe. We wouldn't need to invoke exotic new physics or rewrite our entire cosmological framework. We just need to accept that our galactic neighborhood is far more unusual than we thought. But how do you find a void this massive? It's not like it's labeled in the sky. Astronomers use redshift surveys, mapping out galaxies across the sky and measuring their distances and velocities. What they found is a radial pattern of underdensity extending roughly 1 billion light-years in all directions from the Milky Way. This spherical pattern is what defines the KBC Void. The density of galaxies increases the farther out you look, consistent with the idea that we are inside a giant, underdense bubble. This isn't just an abstract concept. The effects of this void could ripple into multiple areas of physics and cosmology. For instance, if we live in such a void, then it affects how light from distant supernovae reaches us. The light passes through a region with less gravitational lensing and fewer massive structures, which can subtly alter the luminosity and redshift of those sources. That, in turn, influences how we interpret the data. We might be overestimating the acceleration of the universe's expansion, potentially challenging the necessity for dark energy as it's currently understood. Now, let's dwell for a moment on the scale of this void. 2 billion light-years. Let that number soak in. A light-year is about 5.88 trillion miles. Now multiply that by 2 billion. That's the diameter of the KBC Void. It's so vast that if a spaceship traveled at the speed of light, something currently impossible, it would still take 2 billion years to cross from one end to the other. That's nearly a sixth of the age of the universe. And yet, in this unimaginably vast region, there are significantly fewer galaxies than in other regions of similar size. But that emptiness raises another question. How could such a vast underdense region even form in the first place? The standard model of cosmology, known as lambda CDM, describes a universe seeded by quantum fluctuations in the early universe, which were amplified by inflation. These fluctuations led to over- and underdense regions, and over time, gravity pulled matter into clumps, forming stars, galaxies, and clusters. The underdense regions became voids. But for a void the size of the KBC to emerge naturally, the initial fluctuation would have to be enormous, on the level of several standard deviations from the average. Statistically, that makes it incredibly rare. Some have argued that this challenges the Copernican principle, the idea that Earth and humanity are not in a special location in the universe. If we are in one of the largest known voids, then aren't we in a privileged spot? Doesn't that violate the assumption of mediocrity that underlies modern cosmology? Not necessarily. While it's improbable, it's not impossible. Some regions of the universe will be more or less dense than average, just due to the random distribution of fluctuations. And our ability to observe the universe is, by definition, limited to the vantage point of Earth. We could very well be in an unusual region simply by chance. Still, the implications are profound. If we accept that the KBC Void exists and that we are located near its center, then many of the cosmic puzzles we face today might have simpler explanations. The need for dark energy could diminish, or at least its properties might need to be reevaluated. The discrepancies in the Hubble constant could be resolved, and our understanding of the universe's large-scale structure would be dramatically enriched. But let's not stop at the theoretical. Observationally, the evidence for the KBC Void is not universally accepted. Some researchers argue that the underdensity is not as significant as claimed. Others say that while there may be a local void, it cannot account for the full Hubble tension. There's ongoing debate in the astrophysical community about the exact properties, size, and implications of this void. Yet, it continues to capture imaginations and prompt new studies. Let's now turn our minds to what it would actually be like to travel through this void. Picture a spacecraft venturing out from the Milky Way, moving at a fraction of light speed. At first, things look normal, galaxies scattered across the sky like glitter on velvet. But as the craft journeys deeper into the KBC Void, the number of galaxies begins to thin. Stars become fewer. Darkness dominates. The familiar clusters of the cosmic web start to disappear, and silence envelopes the void. It's not the silence of space where sound cannot travel, but a deeper silence, an absence of structure, of matter, of cosmic activity, a silence that is almost existential, a silence that feels like staring into the universe's own abyss. Yet, within this emptiness, there's still much to study. Dark matter is still present. The cosmic microwave background still filters through. Intergalactic gas still drifts in wisps across the dark. gravity still warps space-time. It's not nothing. It's a quieter, more subtle kind of something. And it may hold secrets that challenge our deepest assumptions about the cosmos. Let's dive even deeper into this immense cosmic chasm, the KBC Void, a phenomenon that forces us to reimagine our place in the universe. To understand how unusual such a vast region of emptiness is, consider the average distribution of galaxies in space. In most directions we look, galaxies are sprinkled across the sky with astonishing consistency, forming a lattice of matter interconnected across hundreds of millions of light years. They bunch up in clusters, group together in superclusters, and trace out the shimmering architecture of the universe's large-scale structure. But here, within the boundary of the KBC Void, that elegant distribution collapses into something eerily sparse, an expanse so underpopulated that it becomes statistically anomalous. From the edge of the observable universe to the reaches of our local galactic neighborhood, every part of the cosmos plays its role in telling us how the universe formed and evolved. Yet when we turn our gaze inward, when we scrutinize the space surrounding the Milky Way, we uncover a surprising reality. The evidence compiled by Keenan, Barger, and Cowie revealed that galaxy counts within roughly 300 megaparsecs, or nearly 1 billion light-years in radius, showed a consistent underdensity. That's not just a small dip in population. It's a consistent, deepening void as you move inward. Imagine standing on a hill overlooking a city, expecting to see a glowing sprawl of lights, only to see darkness stretching endlessly in all directions. That's the cosmic equivalent of what we see when we map our galactic environment. But how does this discovery compare to other known voids in the universe? There are indeed many cosmic voids, regions like the Boötes Void, sometimes nicknamed the Great Nothing, which spans about 330 million light-years in diameter. But even that monstrous hole in the galactic web pales in comparison to the KBC Void. It's not just the size that matters, it's the subtlety of the void. Unlike the Boötes Void, which is more clearly delineated, the KBC Void is embedded within the very fabric of our local universe. Its boundaries diffused, its gradients gentle. It does not declare itself with dramatic contrast. It whispers through statistics, hiding in the gradients of redshift surveys and galaxy luminosity functions. The process of discovering such a void is no small feat. It requires thousands of hours of telescope time, precise measurement of redshift for tens of thousands of galaxies, and sophisticated statistical models to interpret the data. Keenan and his colleagues relied on data from surveys like the 2-micron All-Sky Survey, 2MASS, and the Sloan Digital Sky Survey, SDSS, building radial density profiles that spanned enormous cosmic distances. By comparing the expected galaxy density to the observed numbers, they were able to demonstrate a consistent underdensity out to roughly 300 megaparsecs. What's more, the void seemed to be roughly isotropic, meaning it appears the same in every direction from our point of view, a signature suggesting that we may be centrally located within it. This brings us back to the philosophical implications. The Copernican principle, one of the foundational tenets of modern astronomy, asserts that Earth does not occupy a special or privileged position in the cosmos. Historically, this principle dethroned the geocentric model and led to the heliocentric revolution, continuing to guide our thinking to this day. But what if by chance we do occupy a relatively unusual location? Not because the universe is arranged that way on purpose, but simply due to probabilistic variance. Would that really invalidate the Copernican principle, or merely remind us that even in a vast, impersonal cosmos, peculiarities can arise naturally? Statistically, being near the center of a void as large as the KBC might seem improbable, but improbable does not mean impossible. Some simulations have shown that large-scale underdensities can emerge naturally from the stochastic processes that govern the early universe. The cosmic microwave background itself shows tiny temperature fluctuations, reflecting regions that were ever so slightly more or less dense during the epoch of recombination. Over billions of years, those differences were magnified by gravity, leading to the universe we see today, a patchwork of dense filaments and empty voids. The KBC void might simply be one of the larger patches of underdensity in this complex quilt. However, the potential implications of the KBC void stretch far beyond philosophical debate. It has the power to influence our interpretation of dark energy, the mysterious force believed to be accelerating the expansion of the universe. When supernovae observations first suggested that the universe's expansion was speeding up, the astronomical community was stunned. This led to the introduction of the cosmological constant, a term Einstein once discarded as a stand-in for dark energy. But if we live in an underdense region, then light from distant supernovae might be distorted in such a way that mimics cosmic acceleration. In technical terms, the inhomogeneity of the local universe could affect the observed redshifts and luminosity distances of type Ia supernovae, leading us to overestimate their recession speeds. This could produce the illusion of acceleration even in a universe that is expanding at a constant rate. Such models, known as Lemaitre, Tolman, Bondi, LTB models, propose that the universe may not be perfectly homogeneous on large scales, and that local underdensities like the KBC void can have real effects on observational cosmology. While most cosmologists still favor the standard lambda CDM model with dark energy, these alternatives serve as a reminder that assumptions must always be tested, and that even the most widely accepted theories can be challenged by a well-placed anomaly. Of course, for the KBC void to resolve the Hubble tension or impact our understanding of dark energy, it must be properly characterized. Is the underdensity sharp or smooth? Is it spherical or asymmetric? Does it extend equally in all directions? These are not simple questions. The observable universe is finite, and our ability to measure it is limited by the speed of light, observational bias, and cosmic variance. Yet researchers continue to develop more advanced surveys, sharper instruments, and refined statistical models to probe the cosmic neighborhood more deeply. Future missions like the Vera-C, Rubin Observatory's Legacy Survey of Space and Time, LSST, and the European Space Agency's Euclid Telescope aim to map the universe with unprecedented detail. These tools may help confirm the presence of the KBC void or refute it. Either outcome would be scientifically valuable. If the void exists, it may reshape our understanding of cosmic expansion. If it doesn't, then we must look elsewhere for explanations to the Hubble tension and the strange silence of our local universe. In the meantime, simulations and theoretical models continue to play a critical role in exploring the consequences of the KBC void. Cosmologists use in-body simulations to evolve billions of particles under the influence of gravity, constructing virtual universes that can be compared to our own. By introducing large-scale underdensities into these models, scientists can test how such features affect light propagation, redshift measurements, and the structure formation over time. These simulations often reveal subtle effects, such as anisotropies in the cosmic microwave background or peculiar velocities in galaxy flows, that might serve as indirect signatures of the void. But perhaps the most profound implication of the KBC void is what it says about the universe's emptiness. For most of human history, we thought of space as a void simply because it lacked air. But in reality, it is a tapestry woven from galaxies, matter, energy, and dark mystery. To say that space is empty is to misunderstand its complexity. And yet, within the cosmos, there are places that approach true emptiness. Regions so devoid of structure, so bereft of matter, that they are as close as we may ever come to experiencing the nothingness our ancestors imagined. The KBC void is one of those places. From the coldest vacuum to the deepest galactic clusters, the universe is a spectrum of density and form. The KBC void represents one end of that spectrum, a deep, yawning chasm in the cosmos that invites both scientific scrutiny and philosophical awe. It is a cosmic riddle, a data point in an unfathomable equation, a shadow cast across the starlit halls of creation. And we, humanity, might be living right in its center. Let us now move further into the depths of the KBC Void's implications and reach for the very structure of the universe itself. For the story of this underdense region is not merely about a lack of galaxies. It is about the quiet rhythm of the cosmos and how subtle variations ripple through space-time, influencing everything from the birth of stars to the aging of light. To appreciate the KBC Void in the proper cosmic context, we must examine the grand scaffolding of the universe, the cosmic web. This vast framework is composed of filaments, walls, nodes, and voids. It stretches across the universe in a near-invisible lattice, with galaxies clinging to the dense threads of matter like dew on a spider's web. Within this immense structure, voids form naturally in the spaces between these filaments. Most voids are irregular, shaped by the push and pull of gravity from surrounding matter. They range in size, typically measuring tens to hundreds of millions of light-years in diameter. But the KBC Void is different. Its sheer scale, approximately 2 billion light-years across, makes it a statistical anomaly. According to the standard lambda-CDM model, the likelihood of such a massive, spherically symmetric void existing is incredibly low. In fact, some calculations suggest that a void of this magnitude should not exist in our universe unless something unusual has taken place. One explanation is that the universe is far more complex and inhomogeneous than we have previously imagined. While the cosmological principle assumes that, on large scales, the universe is both homogeneous and isotropic, local deviations can and do occur. The existence of the KBC Void could be an extreme case of such a deviation. Some physicists have argued that we may need to revise our understanding of large-scale homogeneity to accommodate this kind of structure. Others argue that the void's presence may point to some overlooked component of cosmic physics, an artifact of dark energy behavior, or an unusual inflationary condition in the early universe. But to explore those possibilities, we must also delve into the realm of cosmological observations. One of the primary methods for probing the large-scale structure of the universe is redshift surveying. As light travels from distant galaxies to our telescopes, the expansion of the universe stretches its wavelength, shifting it toward the red end of the spectrum. By measuring the redshift of thousands of galaxies in all directions, we can map the distribution of matter and detect voids, clusters, and filaments. The KBC Void became apparent not through a sudden absence of light, but through a slow, methodical accumulation of statistical deviation in redshift surveys. When enough galaxy counts were collected, a pattern emerged, one in which the density of galaxies decreased significantly as one moved inward toward the center of our cosmic neighborhood. This has a profound impact on the interpretation of type Ia supernovae. These cosmic beacons are used as standard candles to measure the expansion of the universe because of their consistent intrinsic brightness. If the light from these supernovae passes through an underdense region like the KBC Void, it will be subtly altered, not just in brightness, but in the way it stretches through space-time. The journey of light across billions of years is affected by the gravitational potential it traverses. In underdense regions, there is less gravitational resistance, meaning that photons lose energy more slowly, resulting in redshift patterns that mimic an accelerating universe. This concept leads to what is known as the void model of cosmic acceleration. In this model, the observed acceleration of the universe's expansion is not due to a mysterious form of energy pushing galaxies apart, but rather a consequence of our position within a massive underdensity. The void essentially acts like a giant gravitational lens, distorting our measurements of the universe beyond its boundaries. This idea remains controversial, and while it cannot entirely account for all cosmological observations on its own, it offers a compelling complement to existing theories, and it reminds us to question even our most deeply held assumptions. But the KBC Void is more than a cosmological curiosity. It has the potential to affect galaxy evolution as well. In regions of low density, the gravitational environment is very different. Galaxies and voids tend to be smaller, less massive, and more isolated. Star formation rates may vary, and the chemical evolution of galaxies can be influenced by the availability of gas and the frequency of galactic interactions. In dense clusters, galaxies collide and merge regularly, triggering bursts of star formation and feeding central black holes. In voids, these encounters are rare, and galaxies live quieter lives, evolving in relative isolation. If the KBC Void encompasses our own Milky Way galaxy, as some models suggest, then our cosmic neighborhood may be a relatively tranquil place. This could have implications for the development of life. A less crowded region of the universe means fewer galactic collisions, fewer catastrophic gamma-ray bursts, and a lower frequency of events that could sterilize planetary surfaces. While it would be unscientific to say that the KBC Void caused life to emerge on Earth, it is nonetheless intriguing to consider whether our location in this unusually empty stretch of the universe provided a kind of cosmic shelter during the early stages of our planet's history. On the theoretical front, some physicists have proposed that massive voids like the KBC could be remnants of primordial fluctuations, large-scale variations in density that were seeded during the inflationary epoch, just fractions of a second after the Big Bang. During this period, space expanded faster than the speed of light, smoothing out most of the irregularities in the universe. But tiny quantum fluctuations were stretched to cosmic scales, creating the seeds of all future structure. If, by chance, a slightly larger underdensity formed during this process, it could have grown over billions of years into the kind of void we see today. In this sense, the KBC Void may be a fossil, an imprint of a moment when the universe was still less than a trillionth of a second old. To confirm such theories, researchers are turning to advanced simulations and higher-resolution observations. Projects like the Dark Energy Spectroscopic Instrument, DESI, the Square Kilometer Array, SKA, and the James Webb Space Telescope, JWST, offer tools that can peer deeper into the cosmic past and test the boundaries of current models. These instruments can gather data on the faintest galaxies, measure subtle gravitational effects, and refine our understanding of the universe's expansion history. Meanwhile, efforts to simulate voids continue to refine our understanding of their formation and behavior. Void cataloging has become a field in its own right, with cosmologists using machine learning algorithms to classify and analyze thousands of voids in cosmological datasets. These studies have revealed that voids are not just empty holes. They're dynamic environments where matter flows outward, galaxies evolve differently, and the rules of structure formation take on new forms. The KBC Void, if fully confirmed, would be a cornerstone of this research, a benchmark for testing theories of inhomogeneity, dark energy, and cosmic evolution. And yet, for all our scientific insights, there remains something deeply poetic about the KBC Void. In a universe teeming with galaxies, stars, and the glow of ancient light, here lies a vast, yawning silence, a place where the cosmos has grown quiet. It is a reminder that even the universe has its pauses, its empty halls, its whispered absences. It is in these silences that we sometimes hear the most profound truths, not just about the universe, but about ourselves. For to look into a void is to confront the infinite. It is to ask the question that every civilization must eventually face. Why are we here in this moment, in this place, surrounded by so much emptiness? Perhaps the KBC Void is nature's way of humbling us, of showing us that the universe is not obligated to fill every corner with brilliance, that sometimes emptiness itself is part of the design. And in that design, we may find new meaning, new science, and new questions, ones we have yet to even imagine. And so we return to the KBC Void, not just as a structure of space, but as a narrative thread woven through the tapestry of the cosmos, a hauntingly silent region that challenges our assumptions, bends our equations, and stretches our imaginations to their furthest limits. As we continue this deep exploration, we now move further into the intricate layers of its physical structure, how it was discovered, its implications on cosmological constants, and the multitude of ways in which it influences both local and universal scales. To understand the scale of the KBC Void, we must remind ourselves that we are speaking of a structure so large that light itself, traveling at the fastest speed allowed by nature, would take approximately 2 billion years to cross it. This isn't a minor irregularity in the cosmic web. This is a vast chasm, an underpopulated domain where the density of galaxies and matter is markedly lower than the universal average. In a universe estimated to be about 13.8 billion years old, this void represents a significant fraction of both time and space. If we imagine the universe as a symphony, the KBC Void is a rest, an extended silence that gives definition and contrast to the surrounding melody. The void was first proposed and identified in a 2013 study by Keenan, Barger, and Cowie, hence the name KBC. Their research involved measuring the number and distribution of galaxies in our local universe using redshift surveys and comparing those numbers with more distant galactic regions. What they found was an apparent decline in the density of galaxies within a radius of roughly 1 to 1.5 billion light-years from Earth, suggesting that our position in the cosmos might lie within a vast underdensity. The void itself was estimated to span nearly 2 billion light-years across, potentially making it the largest known structure of its kind. At first glance, this might seem like a statistical fluke. After all, the universe is vast, and our observational tools are subject to limitations. But as more data poured in and more refined models were applied, the evidence for the KBC Void began to solidify. Several independent studies began to arrive at similar conclusions, pointing to a genuine large-scale underdensity centered near our location in the universe. This discovery immediately raised a profound question. What if this void is not just a random feature, but a critical factor influencing our observations of the cosmos? One of the most direct implications of the KBC Void is its potential impact on the Hubble constant, the rate at which the universe is expanding. For decades, astronomers have been trying to pin down this number, and it turns out that different methods produce slightly different results. When measured using the cosmic microwave background, CMB, the afterglow of the Big Bang, the Hubble constant appears to be about 67 to 68 kilometers per second per megaparsec. But when measured using local methods, such as observing type I supernovae, the number is closer to 73 to 74 kilometers per second per megaparsec. This discrepancy, known as the Hubble tension, is one of the most puzzling mysteries in modern cosmology. The presence of the KBC Void may provide a partial resolution. If we live in an underdense region of space, then local galaxies would be receding from us faster than galaxies outside the void due to the reduced gravitational pull within the void. This would cause supernovae and other local distance indicators to appear slightly closer than they truly are, leading to an overestimation of the local expansion rate. In other words, the void stretches not just space, but also our measurements of that space. Still, this explanation is not without controversy. Some cosmologists argue that the KBC Void is not large or deep enough to account for the full discrepancy. Others suggest that the void may need to be integrated into broader models of cosmic variance. The idea that different regions of the universe may naturally exhibit different properties due to early quantum fluctuations and inflationary dynamics. In this view, the KBC Void might be part of a larger mosaic of over- and underdense regions, all contributing in complex ways to the universe's grand behavior. To further test these theories, astronomers have begun refining their models using advanced simulations of cosmic structure formation. These simulations begin with conditions shortly after the Big Bang and evolve according to known physical laws, including gravity, thermodynamics, and general relativity. By tweaking the initial density fluctuations and watching how they grow over billions of years, scientists can create virtual universes that closely mimic the real one. When these simulations are designed to include a large local underdensity, they often produce results that closely match our observations, lending further credence to the KBC hypothesis. Moreover, observations of the cosmic microwave background offer subtle hints about our position within the universe. While the CMB is largely uniform, there are small anisotropies, tiny fluctuations in temperature that represent early density variations. If we were deeply embedded in a void, we might expect to see certain statistical anomalies in the CMB, such as dipole asymmetries or directional dependencies in expansion. Some studies have indeed suggested slight anomalies in the CMB that could be consistent with a local underdensity, though the evidence remains tentative. Beyond measurements of expansion and background radiation, the KBC Void has intriguing implications for gravitational lensing. In general, light from distant galaxies is bent by the gravitational influence of intervening matter, a phenomenon known as gravitational lensing. In dense regions of space, this lensing is strong, causing multiple images, arcs, and distortions. But in underdense regions like voids, the effect is reversed. Light is delensed or spread out due to the weaker gravitational potential. This means that galaxies observed through voids might appear slightly fainter and less distorted, altering our perception of large-scale structure. Measuring these subtle lensing effects is a growing field of observational cosmology and may soon offer additional evidence for or against the KBC Void's existence and scale. There's also the matter of cosmic flow. In our universe, galaxies are not simply drifting along with the Hubble expansion. They're also influenced by local gravitational pulls and pushes. This creates a complex dance of motion known as peculiar velocity. If we live in a large underdense region, then the gravitational pull from surrounding denser regions would subtly accelerate our motion outward, creating a dipole in cosmic flows. Several surveys of galaxy velocities have detected unusual flow patterns that might be explained by a void model, though again, the data is complex and the conclusions tentative. But let us take a step back from the technical details for a moment and consider the philosophical ramifications of this immense emptiness that may surround us. If we are indeed situated near the center of one of the largest voids in the universe, then the Copernican principle, the idea that Earth and its observers are not in a privileged position, may need a subtle revision. While this principle has guided astronomy for centuries, suggesting that we are not the center of anything, the KBC Void implies a potential exception. Though this may not place us in a metaphysical center of the cosmos, it does suggest that our local environment is not typical, and that, in turn, raises profound questions about the anthropic principle, the idea that the universe's properties are as they are in part because they allow for the existence of observers like us. Could it be that the emergence of intelligent life requires not just the right kind of star and planet, but also the right kind of cosmic neighborhood? Might our relatively calm position within a vast void have insulated us from cosmic hazards and provided a stable platform for biological and cultural evolution? These are speculative questions, to be sure, but they resonate with the human urge to understand our place in the universe. The KBC Void also touches on deeper questions of cosmological fate. If we are indeed surrounded by an immense underdensity, and if similar voids permeate the universe, then the overall fate of cosmic structure might be governed not just by expansion, but by the interactions between these vast regions of emptiness and structure. In a far future universe, as dark energy continues to accelerate the expansion of space, galaxies will drift further apart, and the universe will grow colder and more isolated. In this bleak future, the voids may come to dominate, and what we now see as a structured, vibrant cosmos may dissolve into a faint haze punctuated by islands of matter. The KBC Void, in this view, is not just a quirk of local structure. It is a preview of what is to come. And so the KBC Void remains a paradox, an absence that is full of meaning, a silence that speaks volumes, a mystery that invites us to rethink the nature of everything. It challenges our understanding of gravity, expansion, structure, and even life. It is not just a blank spot on the map. It is the map itself redrawn. And as we continue to observe, simulate, and theorize, we must remain open to the possibility that the universe is far stranger and more beautiful than we have ever imagined. As we delve even deeper into the enigma of the KBC Void, it becomes increasingly apparent that what may appear as a cosmic absence is, in fact, an incredibly dynamic and influential player in the grand orchestration of the universe. To call it empty is misleading. It is not a vacuum in the strictest sense, but rather a region with significantly reduced matter density compared to the cosmic average. And this reduction isn't just a minor dip. It could be enough to sway major cosmological constants, distort light from distant galaxies, and subtly shape the very structure of our observable reality. One of the most fascinating aspects of the KBC Void is how it forces us to reevaluate our cosmic frame of reference. Most of our measurements of distance and velocity across the universe rely on the assumption of homogeneity and isotropy, the cosmological principle. That is, the universe should appear roughly the same in all directions and from any point of observation, provided you zoom out far enough. But the existence of such a massive void calls that assumption into question, at least locally. If the KBC Void is real, and if we happen to live relatively close to its center, which observational data suggests, we may be peering out into a universe that is not symmetrical from our perspective. This asymmetry could affect measurements in subtle but significant ways. For instance, if we measure light from galaxies that lie beyond the void, the light has traversed a region of low gravitational potential. This journey changes its redshift slightly compared to if it had traveled through a more average or overdense region. In effect, our measurements could be skewed by the very space through which photons travel. This opens the door to discussions on gravitational redshift effects in voids. Light climbing out of a gravitational well is redshifted, while light falling into a well is blue shifted. In an underdense region, the gravitational potential is shallower, meaning the redshift from light climbing out of it is reduced compared to what we would expect. In practice, this might contribute to the slight overestimation of distances when using standard candles like supernovae, a key component in determining the Hubble constant. On this note, let's revisit the Hubble tension, one of the most contentious debates in modern cosmology. The possibility that the KBC Void may resolve, or at least influence the tension, is compelling. Think of it this way. If the local universe is expanding faster than the average due to the lower gravitational braking force of the void, it would naturally make the locally measured Hubble constant higher. This would reconcile, at least partially, the discrepancy between local measurements and those based on early universe observations like the CMB. Some cosmologists have attempted to simulate such a scenario using the Lemaitre, Tolman, Bondi, LTB models. These are solutions to Einstein's field equations that allow for spherically symmetric but radially inhomogeneous universes, perfect for modeling voids. According to some versions of the LTB model, a large enough underdensity could produce an apparent acceleration of the universe's expansion without requiring dark energy. This is a radical proposition, as it challenges one of the cornerstones of modern cosmology. While the consensus remains strongly in favor of dark energy, these alternative models underscore just how disruptive a structure like the KBC Void could be. Even beyond cosmological constants and observational biases, the KBC Void invites us to think more deeply about how such vast structures could form in the first place. According to the standard model of cosmology, the large-scale structure of the universe emerged from tiny quantum fluctuations in the early universe, amplified by inflation and later shaped by gravity. Over time, denser regions attracted more matter, forming filaments, clusters, and galaxies, while underdense regions emptied out, forming voids. The key question, then, is whether a void as large and underdense as the KBC Void can form naturally under these conditions. Simulations suggest that large voids are not only possible but expected, though the size of the KBC Void still places it at the extreme tail of the distribution. That said, every extreme case pushes the boundaries of our models and invites refinements in how we simulate the cosmos. Another key component in understanding the KBC Void is its relationship with the larger cosmic web, the network of filaments and nodes that make up the large-scale structure of the universe. Voids are not isolated. They exist in a dynamic interplay with the rest of the structure. Where there are voids, there must also be compensating overdensities, superclusters, walls, and filaments. These surrounding structures may in fact exert a gravitational pull on the void, subtly influencing the motion of galaxies within it. The edges of voids are often sites of fascinating cosmic dynamics. Galaxies that lie on the void boundary may experience a form of gravitational drift away from the void's center toward denser regions. This drift could influence not just their positions, but their evolution. Galaxies in lower density environments tend to be bluer, more gas-rich, and more actively forming stars, while those in denser regions are redder, older, and more passive. This correlation, known as the morphology density relation, might find extreme expression in void galaxies. Studying these galaxies could offer rare insights into how environment shapes galactic evolution. Further, researchers are beginning to explore the KBC Void's influence on cosmic microwave background (CMB) anomalies. Though the CMB is primarily a relic of the early universe, it can be subtly distorted by structures it passes through on its journey to us. One such distortion is the integrated Sachs-Wolf (ISW) effect. As CMB photons pass through evolving gravitational potentials, their energy is slightly altered. In voids, this effect can produce small but measurable temperature variations. Some studies have even linked certain cold spots in the CMB to known voids, though attributing these directly to the KBC void remains speculative. In terms of direct observation, much of what we know about the KBC void comes from redshift surveys and galaxy counts. These include the 2-mass redshift survey, 2MRS, the Sloan Digital Sky Survey, SDSS, and the Cosmic Flows Project. These surveys map the positions and velocities of galaxies in 3 dimensions, allowing astronomers to reconstruct the local density field. Advanced statistical techniques, such as Voronoi tessellations and watershed void finders, are used to identify underdense regions and estimate their volumes and depths. As these surveys become more refined, particularly with next-generation telescopes like the Vera-C, Rubin Observatory, the Nancy Grace Roman Space Telescope, and the Euclid mission, we expect our maps of the universe to become more precise. These instruments will help us confirm the true scale, depth, and influence of the KBC void and other similar structures. It may also allow us to compare voids across different redshifts, giving us a dynamic picture of how they grow and evolve over time. Let's also consider the implications for cosmic isotropy. If we are embedded in a void, does that mean the universe is anisotropic on our scales? And if so, how far out do we need to look before the universe begins to appear isotropic again? This question ties into the idea of a homogeneity scale, the scale at which the universe transitions from being clumpy to smooth. Traditional estimates place this scale at around 250 to 300 million light-years, but the KBC void challenges us to reconsider. If underdensities this large are not uncommon, the homogeneity scale may be larger than previously thought. And then, of course, there's the human fascination with being special. If the KBC void centers near us, are we, cosmically speaking, in a special place? The idea tugs at philosophical and scientific threads alike. It revives debates that echo back to Copernicus, Galileo, and Newton, who each helped dethrone humanity from a central position in the cosmos. The KBC void flirts with the possibility that our place might be unusual, not central in a literal sense, but perhaps anomalous in a statistical one. This brings us into the realm of anthropic reasoning. If intelligent observers are more likely to evolve in certain types of environments, then perhaps we shouldn't be surprised to find ourselves in one. Perhaps voids like the KBC act as cosmic cradles for stability and observation, quiet havens in the turbulent ocean of gravitational structure. It's a thought-provoking idea that will surely inspire both theoretical and empirical work for years to come. As we continue observing, modeling, and theorizing, the KBC void stands as a powerful reminder of how much we still don't know. It may be a key to solving the Hubble tension, a a glimpse into the dark underpinnings of structure formation, or a mere statistical fluke inflated by observational bias. Whatever it turns out to be, it is already serving a valuable function by forcing us to sharpen our tools, refine our models, and think more deeply about the cosmic environment that surrounds us. We are not simply observers of the universe. We are embedded within it. The light that reaches us, the structures we infer, the numbers we derive, all of them pass through the filter of space and time we inhabit. And if that filter is shaped by an immense underdensity, a silent abyss spanning 2 billion light-years, then we must account for its influence with care and curiosity. The KBC Void, vast and whispering, beckons us to listen more closely to the dark between the stars. Indeed, the KBC Void is not just a curiosity of cosmic cartography. It is a profound clue, a whisper from the large-scale structure of the universe that something about our understanding might still be incomplete. And in that silence, where galaxies are sparse and distances stretch unfathomably far, the very nature of reality may be etched. To comprehend its impact further, we must explore how voids like the KBC affect not just observational cosmology, but theoretical physics as well. Take, for instance, the role of cosmic voids in testing general relativity. In high-density regions like galaxy clusters, the gravitational interactions are complex and extreme, making it difficult to test relativistic effects in isolation. But voids, by contrast, are simpler, cleaner laboratories for gravitational physics. With lower mass density, the space inside voids offers a purer environment to test how space-time curves, expands, and behaves when matter is nearly absent. Some alternative theories of gravity, including modifications to Einstein's general relativity like F, R, gravity, or scalar tensor models, predict different behaviors in voids and in dense regions. Observing how galaxies move within and around the KBC void, how light is lensed as it passes through, and how the structure evolves over time can all serve as precision tests to confirm or challenge these theories. In this way, the KBC void may not just be a peculiar hole in the universe. It may be a proving ground for the very equations that define cosmic reality. Another fascinating dimension lies in the concept of cosmic flows. The peculiar velocities of galaxies, their motions relative to the smooth Hubble flow, are strongly influenced by the distribution of matter on large scales. If the KBC void truly exists, galaxies in its interior and near its boundary should be flowing outward, pulled by gravity toward denser regions beyond. This large-scale outflow, often called a void flow, is a key signature of such underdense regions. Mapping these flows with high precision provides an independent method to detect voids. Projects like Cosmic Flows 3 and the upcoming Cosmic Flows 4 are dedicated to measuring distances and velocities of thousands of galaxies. The KBC void, by virtue of its enormous size, should leave a detectable imprint on these velocity fields. If the observed motions match predictions from simulations that include a void of that magnitude, it strengthens the case for its existence and character. Now, let us consider one of the most captivating phenomena linked to cosmic voids, gravitational lensing. While voids may seem like the antithesis of massive clusters, which bend light significantly, even low-density regions can subtly warp the paths of photons over long distances. This is called weak gravitational lensing, and its effects are detectable statistically across large surveys. The KBC void, given its size, could exert a measurable weak lensing effect on background galaxies. Observing this lensing not only helps confirm the void's presence, but also informs us about its density profile, how quickly or gradually the density changes from its center to its edge. Understanding this profile is vital because it tells us whether the void is a compensated void surrounded by a shell of overdensity or a more isolated underdensity, each of which has different implications for cosmological models. Moreover, voids influence cosmic structure formation in profound ways. In regions like the KBC void, where gravitational pull is weaker, the formation of galaxies and large structures is delayed or diminished. But the few galaxies that do form in these environments are special. They are often isolated, less affected by interactions and mergers, and retain pristine characteristics of early cosmic conditions. Studying such galaxies, often referred to as void galaxies, can offer a glimpse into primordial star formation processes, gas accretion dynamics, and dark matter distribution. Their simplicity, compared to the chaotic interactions of cluster galaxies, makes them excellent candidates for studying galaxy formation models. In the vast, quiet realm of the KBC Void, the universe's story may be written in more legible ink. As our instruments grow more powerful, we are beginning to observe such galaxies with increasing clarity. Surveys using radio telescopes like the Square Kilometer Array, SK, aim to map hydrogen gas in galaxies across cosmic time. Since hydrogen is the raw material for star formation, such observations can tell us how galaxies in voids differ in their fuel reserves and star formation histories compared to their more crowded counterparts. On a theoretical level, the KBC Void also intersects with discussions about dark matter and dark energy. While it may be tempting to think of voids as simply being empty, they also contain dark matter, albeit at lower densities. But since dark matter interacts gravitationally, its distribution within voids could influence how galaxies are spaced, how light travels, and how cosmic expansion is perceived. There are even more exotic theories that suggest voids might hold the key to understanding dark energy itself. Some researchers propose that the accelerating expansion of a universe, traditionally attributed to a mysterious form of dark energy, might instead be a misinterpretation of large-scale inhomogeneities like the KBC Void. According to this view, if we live in a sufficiently large underdensity, the observed acceleration could be an illusion caused by the way light propagates through a curved and uneven universe. While still a minority view, it is a provocative idea that underscores how important cosmic voids might be in decoding the universe's fate. Now, let us turn to the fascinating question of time. Cosmic voids like the KBC may not only alter our view of space, but our perception of time itself. In general relativity, gravitational potentials affect not just motion, but timekeeping. Clocks run faster in regions of lower gravitational potential. So, if we live in a large void, the rate at which we experience time might be slightly different compared to someone in a denser region. This time dilation is subtle, but over cosmic timescales, it could add up. Such effects, though minute, become significant when measuring the age of a universe, the timing of cosmic events, and the synchronization of observations across different distances. It adds another layer of complexity to the already delicate art of cosmology and further strengthens the argument for understanding voids in intricate detail. Let's not overlook the philosophical implications either. The existence of a massive void in our cosmic neighborhood challenges our assumptions about our place in the cosmos. While we have long rejected the notion that Earth or humanity occupies a special location, the possibility of being near the center of the largest known void rekindles that debate in a new form. Are we in an unusual position? Or is our perspective skewed simply because this is where we happen to be? This leads us to the principle of mediocrity, the idea that there's nothing special about our location in the universe. It's a cornerstone of the Copernican principle, which states that Earth and its inhabitants do not occupy a privileged position. The KBC Void challenges this by suggesting that we might inhabit a region that is in some ways cosmically rare. If so, the consequences ripple through cosmology, philosophy, and even theology. Moreover, studying such a vast underdensity pushes the boundaries of our computational models. Simulating a universe with a void like the KBC requires high-resolution, large-volume simulations that incorporate dark matter, dark energy, baryonic physics, and relativistic corrections. Projects like Illustris, Eagle, and the Millennium simulations are increasingly sophisticated, but the next generation of simulations will need to account for even finer variations in cosmic structure to model voids like KBC with precision. And then there's the question of origin. Why did such a large void form in this particular region of space? Was it the result of random fluctuations amplified by cosmic inflation? Or does it point to some underlying anisotropy in the inflationary field? Some theorists speculate that large voids might be the fossilized imprints of primordial features, ripples, or asymmetries present in the earliest moments after the Big Bang. If so, then the KBC Void could be a fingerprint from the birth of the cosmos, an ancient wound left by the turbulent forces of inflation. It might encode information about the inflationary epoch, the potential landscape of scalar fields, or even the topology of the universe itself. What's more, the KBC Void isn't necessarily unique. As our instruments reach further, we are beginning to detect other large, underdense regions. But what makes the KBC Void particularly intriguing is its proximity. Its influence touches every cosmological measurement we make, from supernova distances to galaxy distributions to the cosmic microwave background. It's not just out there, it's here, shaping our understanding from within. And so, the KBC Void stands not merely as a gap in the galaxy map, but as a cosmic mirror. It reflects the limits of our knowledge, the assumptions we make, and the questions we dare to ask. It invites us to look not just at the stars, but at the spaces between them. Because in those spaces, in the dark, in the silence, in the void, lie the answers to mysteries yet unsolved. As we dive even deeper into the implications of the KBC Void, we find ourselves confronting one of the most provocative and complex questions in all of cosmology. Is the large-scale structure of the universe truly homogeneous and isotropic, or are voids like KBC whispering otherwise? The cosmological principle, the foundational assumption that the universe is uniform and the same in all directions when viewed on a large enough scale, has guided cosmology for over a century. This idea simplifies the mathematical models of the cosmos and allows for elegant solutions, like the Friedmann-Lemaitre-Robertson-Walker FLRW metric, which governs most of modern cosmology. But what happens when something like the KBC Void stretches those assumptions? Can we still say with confidence that the universe is homogeneous when a 2 billion light-year wide underdensity exists in our cosmic backyard? In truth, the KBC Void is pushing cosmologists to refine what they mean by large enough scale. Early models assumed that uniformity emerged at scales above a few hundred megaparsecs. But the KBC Void exceeds those dimensions, suggesting that the scale of true homogeneity might be much larger, or that the universe exhibits statistical homogeneity with large, coherent structures still present. This distinction, though subtle, has major implications. If the universe is only statistically homogeneous, then local regions, such as voids, walls, and filaments, can vary wildly in density, curvature, and expansion rate. This variability must then be accounted for in everything from cosmological redshift calculations to gravitational wave travel times. The KBC Void reminds us that where we are affects what we see, and perhaps even how we interpret the cosmic laws. This also opens a Pandora's box when it comes to understanding cosmological redshift. In a perfectly smooth universe, redshift is solely the result of cosmic expansion. But in a lumpy universe, punctuated by voids and clusters, gravitational effects and local expansion rates can shift photons in more subtle ways. Light traveling from a galaxy through the KBC Void may redshift differently than light traveling the same distance through denser cosmic regions. These inhomogeneities could mimic the effect of dark energy or change our understanding of the Hubble constant. Speaking of which, one of the most pressing issues in modern cosmology, the so-called Hubble tension, might be tied to structures like the KBC Void. The Hubble constant, h, which quantifies the universe's expansion rate, has been measured in different ways with conflicting results. Local measurements using Cepheid variables and supernovae yield higher values than early universe measurements from the CMB via the Planck satellite. Some researchers have proposed that this discrepancy could be explained if we reside in an underdense region like the KBC Void. Within a void, the local expansion rate could be slightly higher due to reduced gravitational deceleration, potentially accounting for the elevated H seen in local observations. Though this explanation isn't universally accepted and requires a void of considerable size and depth, it remains one of the few physical, observational mechanisms proposed to bridge the gap. However, reconciling this with the full suite of cosmological data is no small task. The void would need to be precisely configured to affect only certain measurements without disrupting others, such as the isotropy of the CMB, the baryon acoustic oscillation, BAO, scales, and the abundance of galaxy clusters. This fine-tuning problem adds to the skepticism, but also to the intrigue. The KBC void, whether a full solution or a partial one, remains an unavoidable part of the puzzle. Let us now return to the realm of observational astronomy, where we consider how such voids are identified and mapped. Traditionally, cosmic voids are found using redshift surveys of galaxies. These surveys chart the positions and distances of hundreds of thousands, sometimes millions, of galaxies to construct a 3D model of the universe. Gaps in this distribution signal the presence of voids. However, detecting the KBC void was especially challenging due to its location and scale. It spans a region of space that overlaps with the supergalactic plane and other large-scale structures, making it difficult to distinguish where one ends and the other begins. Additionally, because we're located within or near the void center, our perspective complicates detection. It's like trying to map a vast canyon while standing inside it. Newer surveys, such as those conducted by the Sloan Digital Sky Survey, SDSS, and the Dark Energy Survey, DES, have improved our ability to detect and model such voids. By using machine learning algorithms and sophisticated void-finding techniques, astronomers can now extract the void signature from vast galaxy catalogs. These methods look for topological features, regions with significantly fewer galaxies than their surroundings, and assess the statistical significance of these underdensities. But not all voids are the same. Cosmologists classify them into void-in-cloud and void-in-void types based on the surrounding density environment. A void-in-cloud is a small underdense region surrounded by a larger overdense region. Over time, the pressure from the denser surroundings can collapse the void. In contrast, a void-in-void continues to expand, and its structure becomes more defined. The KBC void appears to be of the latter type, which explains its immense scale and the ongoing expansion of its volume. There's also the matter of how such a void forms in the first place. According to the standard model of cosmology, voids originate from quantum fluctuations in the early universe. These fluctuations were stretched and frozen during cosmic inflation, forming the seeds of future structure. Over billions of years, matter flowed toward overdense regions, leaving underdense voids behind. The larger the initial fluctuation, the larger the resulting void. In the case of the KBC void, simulations suggest that a rare combination of fluctuations could have created such a feature. However, it remains an outlier. The probability of forming a void of this size and depth so close to our location is low under current models, which is why its existence continues to spark debate and drive the development of more refined simulations. But while the physical modeling of the void is crucial, we must also consider the psychological and epistemological implications. The fact that a structure like the KBC void can exist undetected for so long, despite being relatively nearby on cosmic scales, speaks volumes about the limits of our observational reach. It reminds us that cosmic truth is often obscured by perspective, selection bias, and the limitations of our instruments. In a way, the KBC void serves as a cosmic Rorschach test. Different researchers see different implications in its contours. Some view it as a statistical anomaly, others as a key to resolving the Hubble tension, and still others as a warning sign that our models might need serious revision. Regardless of interpretation, it compels us to think bigger, look deeper, and question more thoroughly. It is also a stark reminder that the cosmos is not just filled with light and substance, but shaped equally by emptiness. Voids are not mere absences. They are active participants in the cosmic dance. They shape the trajectories of galaxies, the paths of photons, and the very framework of space-time. In the cosmic web, they are the negative spaces that give the structure its form. And in this immense, enigmatic region we call the KBC Void, the universe invites us to look not just at the stars, but at the silence between them. For in that silence, in that darkness, in that void, may lie the next great revelation. Continuing our deep dive into the enigmatic KBC Void, we now begin to consider the truly profound implications this vast underdensity holds for the broader universe, not just as a statistical outlier, but as a central feature in our evolving understanding of cosmological structure formation, gravitational dynamics, and even the nature of space-time itself. To grasp the full extent of its importance, it's vital to appreciate how voids like KBC interact with the surrounding universe, not in isolation, but as part of a complex, interconnected cosmic tapestry. Though we often discuss the KBC Void as a distinct region, the reality is far more fluid. The boundaries between cosmic structures are rarely clear-cut. Filaments bleed into walls, clusters spill over into sheets, and voids stretch out in diffuse, amoeba-like formations that interlace with each other in ways that challenge our tendency to draw neat borders. In the case of the KBC Void, its environment is particularly fascinating. It is bounded by significant superstructures such as the Sloan Great Wall and the Hercules, Corona Borealis Great Wall, vast filaments of galaxies extending billions of light years. These dense regions help define the contours of the KBC Void, acting as gravitational walls that constrain its growth. But at the same time, the KBC Void appears to push back. Its lower gravitational pull affects the way matter flows in the surrounding regions, subtly distorting the motion of galaxies. Cosmic flows, large-scale movements of galaxies across the universe, are among the most compelling pieces of evidence for the gravitational impact of voids. In areas of higher density, galaxies tend to move inward, pulled by gravity. In voids, the reverse happens. Galaxies move outward, almost as if being repelled. This effect is not due to anti-gravity, of course, but to the relative lack of gravitational attraction in underdense regions. As a result, galaxies on the edge of a void tend to accelerate away from it, creating a phenomenon known as void expansion. This expansion is particularly noticeable in the case of the KBC Void because we appear to be within or near its center. That positioning provides us with a rare perspective. We are not just outside observers, but embedded participants in the dynamics of a void. This complicates our measurements of cosmic parameters, because everything we observe is filtered through our local gravitational environment. The cosmic microwave background, CMB, the redshift of distant galaxies, the timing of type I supernovae, all of it is potentially skewed by our location within this underdense expanse. This leads us to the critical issue of cosmic acceleration and the inferred existence of dark energy. The discovery that the universe's expansion is accelerating, first announced in the late 1990s, revolutionized cosmology. It introduced the concept of a mysterious, repulsive force, dark energy, that now dominates the energy budget of the cosmos. But could part of this apparent acceleration be an illusion caused by our location in a large void like KBC? This idea, while controversial, has been seriously considered by several research groups. If we are in a void, the local rate of expansion could be higher than the global average. This would mean that light from nearby supernovae, which we use as standard candles to measure cosmic distances, would appear dimmer and more redshifted. Not because the universe is accelerating, but because our region is expanding faster than others. Such a scenario would mimic the effects of dark energy without requiring a new fundamental force. However, this explanation requires a delicate balance. The void would need to be just the right size and depth, and we would have to be very close to its center. Otherwise, we would observe anisotropies in the CMB or directional variations in the Hubble constant, which we do not see at a significant level. Moreover, other lines of evidence, such as gravitational lensing, baryon acoustic oscillations, and structure formation models, also point to the need for dark energy, making it unlikely that the KBC void alone can explain cosmic acceleration. Still, the idea is worth exploring because it highlights the intricate relationship between structure and observation in cosmology. It forces us to reconsider the assumption that our measurements represent an average cosmic experience. In reality, every observation we make is filtered through the lens of our local environment. The KBC void, with its immense size and proximity, acts as a kind of natural laboratory for testing these assumptions. Let's now consider another layer of complexity. How do voids like KBC affect the propagation of light? In the standard cosmological model, light travels through a mostly empty universe, occasionally being bent or redshifted by the gravity of intervening matter. But in a universe with massive voids, light can also experience gravitational redshifting and time delays. These effects, though subtle, can accumulate over vast distances. For instance, photons traveling through a void like KBC may gain a slight energy boost as they enter the void and then lose it again as they exit, a phenomenon known as the integrated Sachs-Wolf effect. This interaction between photons and gravitational potentials imprints itself on the CMB, creating faint temperature fluctuations that are detectable with sensitive instruments. By studying these imprints, cosmologists can infer the presence and characteristics of large-scale structures like voids. The KBC void may also play a role in the distribution of cosmic microwave background anomalies. Some unusual features in the CMB, such as the cold spot or large-scale alignments, have been tentatively linked to massive voids. While the connection is still debated, it underscores the need to understand how local structures influence what we observe at the largest scales. But the influence of the KBC void isn't limited to light. It may also affect gravitational waves. These ripples in space-time, generated by violent astrophysical events like black hole mergers, travel across the universe at the speed of light. As they pass through regions of varying density, their amplitude and phase can be altered. In a vast underdense region like KBC, gravitational waves might stretch or distort in ways that change their observed characteristics. This could introduce subtle biases in the inferred distances of sources, which are critical for measuring the Hubble constant using standard sirens. Thus, the KBC void serves as a potential confounding factor not only in electromagnetic observations, but also in gravitational wave astronomy, a field still in its infancy but rapidly expanding. As detectors like LIGO, Virgo, and CAGRA become more sensitive, and as the upcoming LISA mission opens the window to low-frequency waves, accounting for the influence of voids will become increasingly important. All of this paints a picture of a universe as a highly dynamic, structurally rich environment where matter and emptiness interplay in ways we are just beginning to understand. The KBC void stands as a monument to the complexity of cosmic evolution. It forces us to question not only what we know, but how we know it, and what assumptions we must revisit as we push the boundaries of our knowledge. As we peer deeper into the cosmic abyss, guided by ever more powerful telescopes and more precise instruments, the KBC void reminds us that sometimes the greatest mysteries are not hidden in the light, but in the dark. And so, we continue our journey through the immense and mysterious KBC void, a cosmic chasm so vast and so underdense that it challenges our very notions of what the universe is made of, how it formed, and how we interpret the grand data sets of cosmology. To grasp the true scale and significance of the KBC void, we must look beyond its immediate implications and dig into its origins, where such a structure might come from, how it fits into our models of cosmic inflation and large-scale structure formation, and what it can tell us about the evolution of the universe. The origin of voids, particularly one as immense as the KBC void, traces back to the earliest moments after the Big Bang. In the chaotic aftermath of that initial cosmic explosion, the universe was a seething sea of energy and particles. Quantum fluctuations, tiny, random disturbances in energy density, existed even then, minute differences in temperature and density that were barely perceptible. Yet these tiny wrinkles were destined to become the scaffolding for the universe as we know it. As the universe expanded and cooled, these fluctuations were stretched and amplified by cosmic inflation, a brief, exponential expansion that blew up the size of the universe by many orders of magnitude in a fraction of a second. The regions that were slightly denser than average became the seeds for galaxies, clusters, and superclusters. The slightly less dense areas, by contrast, became the beginnings of voids, regions that would never accumulate enough matter to ignite into stars or form galaxies. The KBC Void, therefore, may be the evolved remnant of one of these underdense regions, an ancient emptiness written into the fabric of the early universe. Over billions of years, as matter clumped together into walls and filaments due to gravitational attraction, the voids grew larger and emptier, evacuated by the surrounding density. In a sense, the KBC Void is not just an anomaly. It is a natural consequence of the laws that govern cosmic evolution. But it is its immense scale that stands out. Its diameter, estimated at around 2 billion light-years, makes it perhaps the largest void ever identified. This makes it a statistical rarity, an extreme outlier in the catalog of known voids. The scale of this void challenges the lambda-CDM model, the current standard model of cosmology, which posits a universe composed of roughly 70% dark energy, 25% dark matter, and 5% ordinary matter. In this model, voids are predicted, but the likelihood of one as large as the KBC void is vanishingly small. The existence of such a void suggests that either our observations are skewed by some unknown bias, or the model itself may need refinement. In the realm of science, anomalies are gold mines. They force us to reassess our understanding and look for new explanations that may better describe reality. Another compelling aspect of the KBC void is its role in the ongoing tension between different measurements of the Hubble constant, the rate at which the universe is expanding. As mentioned earlier, local measurements using supernovae and Cepheid variables yield a higher value than those inferred from the cosmic microwave background. If we inhabit a massive underdense region, then our local expansion rate could appear faster than average, which would naturally explain the discrepancy. This theory doesn't eliminate the need for dark energy, but it could alleviate the tension by accounting for environmental effects on our measurements. To explore this further, cosmologists have turned to increasingly sophisticated simulations, virtual universes built from mathematical models and run on supercomputers. These simulations begin with the physics of the early universe and evolve over time according to the laws of gravity, hydrodynamics, and quantum mechanics. When researchers input slight variations in density and matter distribution, they can watch as galaxies, clusters, and voids emerge. Intriguingly, some simulations do produce voids approaching the scale of KBC, but they are extremely rare and require fine-tuned initial conditions. This suggests that if the KBC void is real, it might represent one of the most extreme outcomes of natural cosmological evolution, or it might point toward new physics that better accounts for such outliers. Now, let's take a closer look at the observational data that support the existence of the KBC void. One of the key tools used is galaxy surveys, massive efforts to catalog the locations and velocities of millions of galaxies. By mapping the three-dimensional positions of galaxies across the sky, astronomers can construct a cosmic web that shows where matter is concentrated and where the empty spaces lie. The Sloan Digital Sky Survey, SDSS, and the 2-Mass Redshift Survey are among the major projects that help define the boundaries of the KBC void. These maps reveal a striking underdensity in the direction corresponding to our local region, extending for billions of light years. However, confirming that this region is truly underdense requires more than just counting galaxies. One must also consider redshifts, how the light from galaxies is stretched due to the universe's expansion. Redshifts help determine not just the distance of galaxies, but also the rate at which they're moving away from us. By studying these velocities, scientists can infer the gravitational environment of the region. A consistent pattern of galaxies flowing outward suggests a lack of gravitational pull, consistent with the idea of a void. Moreover, gravitational lensing provides an independent method to estimate mass distribution. Light from distant galaxies is subtly bent as it passes through the gravitational fields of intervening matter. In regions of high mass, this bending is pronounced. In underdense regions, it is minimal. Studies of weak gravitational lensing in the direction of the KBC void show less distortion than expected, further supporting the idea of a mass deficiency. Beyond the observational, there are philosophical implications as well. The Copernican principle, one of the cornerstones of modern cosmology, states that Earth is not in a special or privileged position in the universe. We assume that the cosmos is homogeneous and isotropic on large scales, that no point is significantly different from any other. But the existence of the KBC void, combined with our apparent location near its center, challenges this assumption. If we're in a special place, how does that affect our theories about the universe? It's possible that our local universe is more complex than we thought, and that what we've considered to be universal constants may be subtly influenced by our position. If so, we might need to revise how we model cosmological parameters, taking into account the local structure around us. This doesn't mean the Copernican principle is wrong, but it may be an approximation rather than an absolute truth. Furthermore, the KBC void has opened doors to speculation about other exotic possibilities. Could voids serve as evidence for multiverse theories, where different regions of space have different properties? Could the void be a remnant of a cosmic bubble collision, where our universe intersected with another during the inflationary period? While these ideas are highly speculative, they highlight the richness of inquiries sparked by anomalies like the KBC void. As we continue to map the cosmos with greater precision, future missions like the Euclid Space Telescope and the Vera Rubin Observatory will offer unprecedented views of the large-scale structure of the universe. These instruments will allow us to refine our measurements of galaxy distribution, gravitational lensing, and cosmic expansion, helping to either confirm or refute the nature of the KBC void. But even if future observations modify our understanding of this specific void, the KBC void has already served an invaluable role in pushing the boundaries of cosmology. It has encouraged scientists to think more critically about the assumptions underlying their models, to explore new methods of analysis, and to remain open to the possibility that the universe is stranger than we ever imagined. In that way, the KBC void is more than just an empty place. It is a wellspring of questions, a cosmic mystery that beckons us to look deeper, think harder, and never stop exploring. The story of the KBC void is far from over. It's not just an observational oddity or a blip in a data set. It is an open gateway into reimagining the universe's architecture, an astronomical puzzle that provokes fundamental questions about cosmic symmetry, galactic motion, and the very texture of space-time. As we deepen our dive into its mystery, we must explore further implications, alternative theories, and fringe possibilities, each offering a distinct perspective on what the void could be, how it formed, and what it truly reveals about our universe. To understand just how perplexing the KBC void is, consider its juxtaposition against the cosmic microwave background radiation, CMB. The CMB is the afterglow of the Big Bang, a fossilized snapshot of the early universe frozen in time. It is our deepest and most ancient view of the cosmos, revealing how matter and energy were distributed about 380,000 years after the Big Bang. The CMB is remarkably uniform, showing temperature fluctuations on the order of only 1 part in 100,000. Yet, some researchers have noticed a cold spot in the CMB, a region where the temperature is slightly lower than the surrounding area. This anomaly has intrigued cosmologists for years. Some have speculated that the KBC void might be responsible for this cold spot. The idea is rooted in the integrated Sachs-Wolf effect, where photons from the CMB lose energy while climbing out of large underdense regions, appearing cooler to observers on Earth. If the KBC void lies along the line of sight to the cold spot, this could explain the temperature anomaly. However, this explanation is still debated. The cold spot could also be a statistical fluke or caused by something else entirely. Still, the possibility that a structure as vast as the KBC Void might imprint itself on the CMB is profound. It would mean that voids are not just local features, but cosmological influencers reaching across billions of light years and billions of years of time. Let's now consider the more speculative but fascinating notion of whether the KBC Void could serve as a portal. Not literally like something from science fiction, but metaphorically a window into alternate formulations of gravity. Some theories suggest modifications to general relativity that account for cosmic acceleration without invoking dark energy. These alternative gravity models, such as MOND, modified Newtonian dynamics, or TeVis, tensor, vector, scalar gravity, offer tweaks to how gravity behaves at large scales. If a structure like the KBC Void truly exists and causes the kind of observable effects it seems to, it might provide real-world test cases for these theories. What if gravity behaves differently inside a massive void? What if space-time is subtly curved in a way our models have not yet fully accounted for? These are not mainstream ideas, but the KBC Void forces us to ask, what assumptions are we making about the universe that might be incorrect or incomplete? Now, let's consider the human angle. For those of us on Earth, floating in this vast sea of stars and galaxies, the idea that we may reside within a cosmic bubble is both humbling and profound. We are not at the center of the universe in any privileged way. But if our local galactic neighborhood happens to be situated near the center of the KBC Void, then our cosmic address is uniquely positioned to skew our perception of reality. Everything we measure, from the motion of galaxies to the rate of expansion of the universe, is filtered through the lens of our environment. We often think of telescopes as time machines, showing us what the universe looked like billions of years ago, and this is true. But they are also funhouse mirrors, distorting light and distance according to the mass and voids through which photons travel. Imagine trying to measure the properties of a city from within a deep valley, where buildings appear shorter and more distant due to the terrain. In a similar way, our placement within a vast underdense region could mean that our cosmic measurements are subtly biased. It's not a mistake. It's just a reminder that perspective matters, even on a galactic scale. And this has real consequences. The tension over the Hubble constant, for example, isn't just an academic debate. It influences our estimates of the universe's age, the nature of dark energy, and the ultimate fate of the cosmos. If we can resolve this tension by accounting for our position within the KBC Void, we gain a clearer, more accurate understanding of cosmic evolution. If not, then the discord may point us toward new physics waiting to be discovered. There is also an aesthetic elegance to voids. While we often focus on luminous galaxies and energetic phenomena like quasars, voids represent the quiet side of the universe, the absence that gives structure its meaning. Just as silence gives music its rhythm, voids give form to the cosmic web. Without them, the universe would be an undifferentiated smear of matter. It is the contrast between fullness and emptiness that creates the intricate, lace-like structure of the cosmos. The KBC Void is the most dramatic expression of this contrast. Its sheer scale evokes a kind of awe, a reminder that the universe is not merely a collection of objects, but a living architecture designed by the invisible forces of gravity, dark energy, and cosmic expansion. In this architecture, emptiness has shape, meaning, and influence. From a statistical standpoint, the existence of such a void is rare, but not impossible. Cosmologists use computer simulations to generate many model universes and compare them to our own. In some of these simulations, voids as large as the KBC Void do appear, but they are outliers occurring in only a small percentage of runs. This leads to a fundamental question in cosmology. Do we live in a typical universe or an atypical one? If we keep finding anomalies, large voids, cold spots, unexpected flows, then perhaps the standard model needs adjustment. But what if there's a more exotic explanation? Could the KBC Void be the aftermath of a cosmic phase transition, a shift in the properties of the vacuum that occurred long after the Big Bang? Could it be a relic of symmetry breaking in the early universe, where different regions settled into different quantum states, leaving behind bubbles of low density? Some string theory models allow for such possibilities. These ideas are speculative, yes, but the KBC void gives them a point of contact with observable reality. There are also anthropic considerations. If large voids can skew observations and make the universe appear to be expanding faster than it really is, then perhaps intelligent observers are more likely to evolve in such regions. Places where the expansion rate is high, star formation is relatively tranquil, and gravitational interactions are less chaotic. This could explain why we find ourselves in a void and not a dense cluster. It's a controversial idea, invoking the so-called anthropic principle, which suggests that the universe appears the way it does because observers like us can exist only in certain conditions. While this line of thought is contentious, it underscores how deeply the KBC void touches on foundational questions, not just about the cosmos, but about consciousness and existence itself. Looking forward, the investigation of the KBC void continues on multiple fronts. Astronomers are working to refine distance ladders, the methods by which we measure how far away celestial objects are. This includes the use of standard candles like Type Ia supernovae, as well as surface brightness fluctuations, gravitational waves from neutron star mergers, so-called standard sirens, and time delay lensing of quasars. These diverse tools help to cross-check our measurements and detect whether local expansion rates are truly higher. New skies surveys, such as those from the Euclid Space Telescope and the Vera C. Rubin Observatory, will offer high-resolution, wide-field maps of billions of galaxies. These datasets will allow cosmologists to trace the structure of the cosmic web with unprecedented detail, potentially confirming the size and scope of the KBC void or ruling it out entirely. If confirmed, we may even find other voids of comparable scale, hinting at a larger pattern of underdense regions. Whether the KBC void is a unique structure, a statistical fluke, or a clue to new physics, it has already achieved something remarkable. It has made us question our assumptions, refine our methods, and look at the universe with renewed curiosity. It has reminded us that even in the vast silence of space, there is a story, a narrative of formation, expansion, and the unseen forces that shape everything. The KBC void is not empty. It is full of questions. And in the pursuit of answers, we continue our exploration, not just of the cosmos, but of the limits of human understanding. As we continue this odyssey into the depths of the KBC void, we must now begin to consider its origin story. How could a region so vast, some 2 billion light-years across, and so underdense have come to exist in a universe that began in a relatively homogeneous state? This question drives us into the early universe, where small quantum fluctuations expanded, cooled, and eventually formed the seeds of cosmic structure. The standard model of cosmology, often referred to as lambda CDM, tells us that shortly after the Big Bang, the universe underwent a period of rapid inflation. During this inflationary epoch, tiny quantum fluctuations were stretched across enormous scales. These fluctuations were minute variations in density, and as the universe cooled and matter began to clump under gravity, those slight over and under densities became the foundation of the large-scale structure we observe today: galaxies, clusters, filaments, and yes, voids. In this context, voids are not errors or accidents. They are expected byproducts of the universe's evolution. However, the KBC void challenges even this well-accepted understanding because of its sheer scale and depth. The voids predicted by simulations of the standard model are typically hundreds of millions of light-years across. The KBC void, at 2 billion light-years in diameter, is larger than what is usually generated by our best computational models. This doesn't mean it's impossible under lambda CDM, but it's rare, extremely rare. So, one of the biggest questions becomes, is the KBC void the result of an unlikely but not impossible fluctuation? Or is it the result of physics we don't yet fully understand? Some cosmologists have posited that we might need to rethink how we calculate the probability of such structures forming. Our universe is large, possibly infinite, and rare events do occur when given enough space and time. But if we keep uncovering more and more large-scale anomalies, like the Sloan Great Wall, the Hercules Corona Borealis Great Wall, or the KBC Void, it may indicate that something is missing from our current theory. We also need to consider the growth history of voids. Unlike overdense regions that attract matter, voids are zones where matter drains out. Gravity doesn't work in reverse here. But because voids contain less mass, the surrounding regions pull matter away more effectively. This creates a dynamic expansion process. The void not only remains underdense, it grows. The galaxies within it move away from the center, increasing the void size over time. But in the case of the KBC Void, the underdensity is not merely geometric. It's dynamically significant. It appears to be influencing galactic velocities, expansion rate measurements, and perhaps even cosmic flows. This brings up the notion of peculiar velocities, movements of galaxies that deviate from the overall Hubble flow due to gravitational influences. If we are located within or near the center of the KBC Void, then the peculiar velocities we observe around us might be skewed in ways we have yet to fully disentangle. Let's explore another subtle effect, the kinetic Sunyaev-Zeldovich effect. This phenomenon occurs when cosmic microwave background, CMB, photons interact with moving clusters of galaxies, gaining or losing energy depending on the direction of motion. If large-scale structures like voids or superclusters cause coherent motions over great distances, they might leave imprints in the CMB that we can detect. Observing these effects could offer an independent confirmation of the KBC Void's existence and influence. Now, step back and consider the philosophical implications. What does it mean for humans, confined to a tiny blue planet orbiting an average star, to detect and study a structure that spans 2 billion light-years? It is a staggering thought. The photons we capture from distant galaxies have traveled through space for billions of years, traversing voids and filaments, weaving through the cosmic web to arrive in our detectors. These tiny packets of light carry encoded messages about density, motion, distance, and time. And among the vast data they bring us is the shadow of a void, a silence carved into the fabric of space. In a way, studying the KBC Void is like reading a chapter of the universe that was never written in ink, but in the absence of words. It's a void not just of matter, but of immediate clarity. Every theory we propose, every dataset we collect, every simulation we run, these are our attempts to read that unwritten chapter. And what we find is that even the universe's silences have meaning. Let's push further into the mathematical realm for a moment. One tool cosmologists use to describe the geometry of the universe is the metric tensor, which encodes how distances are measured in curved spacetime. In general relativity, mass and energy determined the curvature of spacetime. So an underdense region like the KBC Void has less mass than surrounding areas and therefore exhibits less curvature. This reduced gravitational pull causes light and matter to behave differently inside the void. In simulations, we can see how light rays bend or don't bend as they pass through such a region. This is called gravitational lensing, and it's one of the tools used to map voids. Unlike massive clusters that bend light inward like a magnifying glass, voids do the opposite. They slightly diverge light like a lens of air and water. This creates subtle distortions in the shapes of background galaxies, an effect that can be measured statistically across millions of observations. In recent years, weak lensing surveys have provided indirect evidence for the existence of the KBC Void by revealing these minute distortions. But again, we run into a dilemma. The data isn't conclusive. Some studies suggest that the KBC Void is real and significant. Others argue that it's an artifact of our observational limitations, a misinterpretation of incomplete data. This is where machine learning and AI enter the picture. With the massive influx of cosmological data from new telescopes, Algorithms trained on simulated universes can help distinguish real features from noise. Already, AI is being used to map voids, classify galaxy morphology, and even predict where to look next. As our tools grow more powerful, so too does our vision. The upcoming Nancy Grace Roman Space Telescope, formerly known as WFIRST, promises to survey the sky with unprecedented precision. Its data may help settle the debate over the KBC Void. Similarly, the Square Kilometre Array, a massive radio telescope project being built in Australia and South Africa, will observe hydrogen gas across the universe's history. These observations could trace the evolution of voids from infancy to maturity, providing new insights into how the KBC Void and others like it formed and grew. Now consider this. What if voids are not merely the absence of matter, but the result of repulsive forces in the universe? This leads us into the domain of dark energy and quintessence, the hypothetical field that drives the universe's accelerated expansion. In some models, dark energy is not a uniform property of space, but a dynamic field that varies over time and space. If so, then perhaps the KBC Void marks a region where this field behaves differently. Perhaps it is a scar, a relic of a phase transition in dark energy's evolution. While speculative, such ideas open the door to a richer, more nuanced understanding of cosmic history. In the years ahead, cosmology will face a choice: hold tightly to the standard model or allow room for radical ideas. Void-centric models, inhomogeneous cosmologies, or modifications to gravity. The KBC Void stands at the center of this debate, not just as an astronomical feature, but as a crossroads of theory and observation. We must also remember that science progresses not just through answers, but through the questions we dare to ask. The KBC Void is one such question, a massive, quiet inquiry written into the heavens. It challenges us to refine our tools, rethink our models, and expand our imagination. And in doing so, it brings us closer to the truth, not just about the universe, but about ourselves and our capacity to understand the unimaginable. As we plunge even deeper into the enigmatic presence of the KBC Void, we must begin to confront the profound cosmological implications it has for not only how we view the large-scale structure of the universe, but how we define our place within it. The KBC Void is not just a celestial curiosity. It is potentially one of the most significant indicators that the universe may not be as isotropic and homogeneous as we have long assumed. This assumption, one of the key tenets of modern cosmology, is known as the cosmological principle, which posits that on sufficiently large scales, the universe looks the same in every direction and from every vantage point. Yet if the KBC Void is real and as vast and deep as the observational data suggests, it directly challenges the cosmological principle. If we are inside or near the center of such a massive underdense region, then our local observations, including those related to the Hubble constant, supernova redshift data, and the anisotropies in the cosmic microwave background, may be biased by our peculiar location. This has enormous ramifications. Much of our understanding of dark energy, cosmic expansion, and the age of the universe is built on the assumption that we are observing from a typical location. But if we are instead observing from a massive void, then perhaps what we interpret as universal expansion acceleration is, at least in part, a local effect caused by our underdense surroundings. This perspective has given rise to what's known as the Hubble bubble hypothesis. The idea is that measurements of the local expansion rate, the Hubble constant, are artificially inflated due to our position within a large underdense region. In essence, the expansion inside a void is faster than in the denser cosmic average because there's less gravitational deceleration. Thus, when astronomers measure the rate of expansion using nearby supernovae, they may detect a higher value than what is calculated from cosmic microwave background measurements originating from much larger scales. The Hubble tension, the discrepancy between the locally measured Hubble constant and the one derived from early universe observations, has become one of the most pressing problems in cosmology today. The KBC void may provide a partial explanation for this tension. If our region of space is underdense by 20 to 30%, as some models suggest, that underdensity could cause a measurable increase in the apparent expansion rate. This wouldn't eliminate the discrepancy entirely, but it could reduce it significantly, potentially bridging the gap between local and global measurements. The implications are staggering. They suggest that some of our most foundational cosmological constants might not be constant at all, but locally influenced. It means that where we are in the universe does, in fact, matter, a notion that contradicts centuries of thinking dating back to Copernicus. The KBC void may subtly be pulling us back into a more geocentric mode of thought, not because Earth is at the center of the cosmos, but because its position in a vast cosmic void is not as neutral or average as previously thought. But how certain are we of the KBC void's dimensions and density profile? Observationally, voids are notoriously difficult to characterize. Galaxies are sparse within them by definition, making it hard to establish statistical significance with sparse data points. To map a void like the KBC, astronomers rely on massive redshift surveys, tracking the three-dimensional positions of tens of thousands of galaxies and reconstructing the density field of the cosmos. The most comprehensive surveys, like the Sloan Digital Sky Survey, SDSS, and the 2-micron All-Sky Survey, 2MASS, have been instrumental in detecting large-scale features like the KBC void. But with new tools like machine learning and advanced simulations, researchers can now better refine the parameters of such voids. Simulations based on lambda-CDM cosmology can generate virtual universes that can be probed for void structures, and these can then be compared to observational data. If the simulations produce voids as large as the KBC void with any regularity, it may indicate that such structures are rare but plausible. If they do not, it may suggest a breakdown in our theoretical framework or signal the need for new physics. There's also the question of how such a void interacts with the cosmic web. We often think of the universe's structure as a three-dimensional spiderweb, galaxies strung along filaments that intersect in dense nodes called clusters, with vast voids in between. The KBC void, however, is so massive that it may act like a gravitational sinkhole, subtly pulling nearby matter toward its edges and shaping the flows of galaxies on enormous scales. This could create detectable anisotropies in the large-scale motion of galaxy clusters, sometimes referred to as cosmic bulk flows. If such bulk flows are aligned with the KBC void, it provides indirect evidence of its influence. These are not motions caused by the overall expansion of the universe, but rather by local gravitational interactions on very large scales. Such flows are hard to measure, as they require precise distance and velocity measurements of galaxies spread across vast areas of the sky. Nonetheless, emerging techniques are improving our ability to detect these flows, and several studies have shown tentative alignments consistent with the KBC void hypothesis. But not everyone agrees. Some cosmologists argue that the statistical significance of the KBC void is still too low to draw definitive conclusions. Others believe that the observed data can be explained without invoking such a massive void. They point to systematic errors in distance measurements, calibration issues with type Ia supernovae, and selection biases in galaxy surveys. In this light, the KBC void might be less of a physical feature and more of an observational artifact. However, these criticisms must themselves confront an uncomfortable reality. If the KBC void doesn't exist, then we must find some other mechanism to explain the persistent anomalies in the Hubble constant, the alignment of cosmic flows, and other large-scale irregularities. The universe, it seems, refuses to conform to our tidy models. The study of the KBC void is not just an academic pursuit. It is a philosophical confrontation with the limits of human understanding. It forces us to acknowledge that even our best theories, our cherished equations and elegant models, are only approximations of a reality that is deeper, stranger, and more complex than we can currently fathom. When we gaze into the vastness of the KBC void, we're not simply looking at a dark region of space. We are peering into a riddle that stretches across 2 billion light years. A riddle written in the language of light, gravity, and time. It's a cosmic whisper that tells us we are not done asking questions. That the universe has more secrets to share. That the silence of the void is, in truth, the loudest message of all. And so we continue, astronomers, physicists, philosophers, dreamers, charting the darkness not to escape it, but to illuminate the space between the stars. The KBC Void is not an absence. It is a presence, haunting and magnificent, that beckons us ever further into the unknown. Even as we attempt to grasp the magnitude of the KBC Void, we must now turn our attention to its implications on light itself, on how photons traverse this immense underdense region of the cosmos, and what it means for our interpretation of the universe's age, size, and rate of expansion. One of the most compelling aspects of this region is how it interacts with cosmic light, particularly the light from type I supernovae, the cosmic standard candles we use to measure vast distances. As photons travel through space, they are affected by the gravitational potential of the regions they pass through. In denser regions, gravity can slow them down slightly, redshift them, or bend their path. In underdense regions, like the KBC Void, there's less gravitational interference, meaning photons travel faster in relative terms and experience less gravitational redshifting. This is a subtle but measurable effect. The photons may arrive slightly earlier, slightly redshifted in ways that mimic cosmic acceleration. This leads to a critical implication. The presence of a large void could produce apparent signatures of accelerated expansion even in a universe that is expanding at a steady rate. This was one of the reasons why some cosmologists in the early 2000s considered void-based models as alternatives to dark energy. Let's be clear, the idea that dark energy might be an illusion caused by our location within a massive void is controversial, but not without merit. In this line of reasoning, the observed acceleration of the universe is not due to an unknown repulsive force permeating all of space, but rather an observational artifact of our peculiar location. In such models, known as inhomogeneous cosmologies, the universe is not viewed as a uniform balloon expanding in all directions, but more like Swiss cheese, dense regions surrounded by vast voids. And if our galactic neighborhood happens to lie inside a large enough void, the rate at which light reaches us from outside might be misinterpreted, leading to the illusion of acceleration. Of course, the lambda CDM model, the current standard cosmological model that includes dark energy in the form of the cosmological constant, is still the dominant paradigm. It explains a wide range of observational data with impressive accuracy. But the tension between the local and global measurements of the Hubble constant continues to persist. Each time we refine our measurements, hoping the discrepancy will vanish, it instead grows more robust. And that is why the KBC Void continues to attract interest, because it may be the missing piece in an increasingly puzzling cosmic jigsaw. The conversation then naturally shifts to methodology. How do we even detect such an enormous structure as the KBC Void, let alone measure its density? Astronomers rely on extensive galaxy redshift surveys, mapping the location and velocity of galaxies in three-dimensional space. By measuring how far away galaxies are and how fast they're moving, we can reconstruct the underlying density field. In the case of the KBC Void, data from the 2-mass redshift survey and similar efforts revealed a large underdensity in the direction of a local void, extending billions of light years and covering a region centered roughly around our own position in the universe. Interestingly, the very idea that we might be near the center of such a void adds another layer of controversy. It invokes a return to a sort of special position for Earth or our galaxy, something that scientists have been reluctant to accept since the time of Copernicus. The Copernican principle, after all, suggests that we are not in a special or privileged place in the universe. To argue otherwise, especially based on observational data, requires extraordinary evidence. And yet, the more data we gather, the more it seems to support the existence of a vast underdensity surrounding us. The key to verifying the KBC void lies in combining multiple strands of evidence. One is the distribution of galaxies. Another is the observed bulk flow of galaxy clusters, large-scale motions that can be influenced by gravitational imbalances. Still another is the anisotropy in the cosmic microwave background. If the KBC void exists, it would affect the temperature fluctuations in the CMB through the integrated Sachs-Wolf effect, where photons climbing out of underdense regions lose energy, leading to tiny cold spots in the CMB map. These subtle signatures are incredibly hard to detect, but provide valuable clues. Then there is the gravitational lensing signal. Dense regions bend light more strongly. Voids do so less. By analyzing the gravitational lensing patterns from distant galaxies behind the proposed location of the KBC void, astronomers can indirectly infer the density profile of that region. Initial findings suggest a lower lensing signal consistent with a large-scale underdensity, lending further credibility to the void hypothesis. Now let's delve into how the KBC void fits into the broader cosmic architecture. The universe is not random. It is organized into a vast and intricate web of filaments, clusters, and voids. The largest structures we know of, like the Sloan Great Wall and the Hercules Corona Borealis Great Wall, stretch for billions of light years. But voids, though empty in a conventional sense, are just as crucial in shaping the universe's layout. They push on the filaments and walls, creating the framework of the cosmic web. The KBC void is different because of its proximity. It's not something we observe in the distant universe. It's something we are potentially inside. That makes studying it both easier and harder. Easier because we can gather more precise data in nearby space. Harder because being inside the structure distorts our ability to view it objectively. It's like trying to understand the shape of a building while standing in one of its rooms. You see the walls and the corners, but you lack the external perspective needed to grasp the full architecture. To get around this limitation, researchers employ advanced computer simulations that replicate various density profiles and expansion rates. By inputting different assumptions about the size and depth of the KBC void, they can model the expected impact on supernova data, CMB fluctuations, and galaxy flows. They then compare these simulations to actual observations, looking for a best fit match. Many of these studies find that a void of the scale and depth proposed by Keenan, Barger, and Cowie can indeed account for several anomalies. Still, not all cosmologists are convinced. The debate continues, fueled by better instruments and more refined data with each passing year. What does the KBC void mean for humanity? For the human quest to understand the cosmos? It reminds us that we are still learning, still reaching, still humbly trying to place ourselves in a universe that is larger, darker, and stranger than any myth ever imagined. The KBC void is not an empty space. It is a frontier. A place where science meets mystery, where data brushes against the veil of the unknown. We may never know exactly what lies at the heart of this vast void, but in studying it, we take another step toward understanding the structure and fate of the universe itself. The questions it raises about our place, about cosmic expansion, about the very nature of time and space, are not just scientific. They are philosophical. They ask us to confront the boundaries of our knowledge and to be okay with the vastness of what we do not yet understand. So we peer into the KBC void, not in fear, but in wonder. It is a silent expanse, yes, but one that speaks volumes. And so, we stand at the edge of cosmic mystery, gazing out into the KBC void, an ocean of emptiness that quietly yet profoundly challenges the foundations of our cosmology. The silence of this immense underdense region, stretching nearly 2 billion light-years across, is not merely the absence of galaxies, gas, or matter. It is a silence that echoes questions we've yet to answer and forces us to re-evaluate assumptions long held as pillars of modern astrophysics. To further understand the enormity of what the KBC void implies, we need to explore how it affects the mathematical and physical frameworks that govern our understanding of cosmic expansion. In traditional cosmological models, specifically the Friedman, Lemaitre, Robertson, Walker, FLRW metric, the universe is treated as homogeneous and isotropic. This elegant simplification allows physicists to use powerful equations to model the universe as if it were the same in every direction and every location. But the existence of something as massive and underdense as the KBC Void adds an undeniable complexity to this framework. Homogeneity begins to fray at the edges when we accept the reality of local voids. And if the KBC Void is as real and significant as data suggests, it introduces a perturbation to the FLRW model. Essentially, local underdensities cause the light from distant galaxies to redshift differently than it would in a uniform universe. This isn't just a minor correction, it has sweeping implications. The very notion of cosmic acceleration, one of the key discoveries of modern astronomy, may need to be partially reinterpreted through the lens of our cosmic location within a density gradient. Here, the role of inhomogeneous cosmologies becomes central. Models such as the Lemaitre, Tolman, Bondi, LTB, solution to Einstein's field equations permit us to study spherically symmetric universes with radially varying density. In these models, observers placed within a void will measure different cosmological parameters than those placed outside it. That means the values we obtain for the Hubble constant, the deceleration parameter, or even the age of the universe could all be biased due to our peculiar placement within the KBC Void. This brings us to the crux of the Hubble tension. A persistent discrepancy between the value of the Hubble constant obtained from the early universe via the cosmic microwave background, particularly through the Planck satellite data, and the value obtained from late universe measurements, such as those using type I supernovae. The early universe suggests a Hubble constant around 67 kilometers per second per MPC, while late universe measurements put it closer to 73 kilometers per second per MPC. This difference has grown increasingly significant as measurement techniques have improved and uncertainties have diminished. If the KBC Void exists and we reside somewhere near its center, the local underdensity could be responsible for inflating our local measurement of the Hubble constant. Light from distant supernovae would travel through regions of lower than average density, arriving slightly sooner and appearing more redshifted than expected. That would make the universe appear to be expanding faster from our vantage point. While this doesn't necessarily eliminate the need for dark energy, it offers a partial resolution to the tension, shifting some of the explanatory burden onto large-scale structure rather than invoking unknown forms of energy. But we cannot take such a hypothesis lightly. The implications of abandoning or modifying the cosmological principle are profound. Doing so could unravel the neat tapestry of standard cosmology and plunge us into a more chaotic, more variable cosmic terrain. Yet the evidence for inhomogeneities like the KBC Void and their potential to influence our measurements demands attention. The philosophical ramifications of this are equally striking. For centuries, we have attempted to remove humanity from any special place in the universe. Copernicus displaced Earth from the center of creation. Later, Hubble showed that the Milky Way was just one galaxy among billions. Now, data from the KBC Void suggests we might once again be in a cosmologically distinct location, not the center of the universe, but the center of a vast void. If this is true, it wouldn't necessarily contradict the Copernican principle, but it would compel us to refine our understanding of what non-special really means in a complex and irregular universe. Let's now return to the observational front. The identification of the KBC Void was not done through a single telescope or a single survey. It emerged from an accumulation of evidence across multiple platforms. One of the key data sets was the 2 Mass Redshift Survey, which mapped galaxies out to redshifts of 0.1, approximately 1.3 billion light-years. This survey showed a decline in galaxy density centered roughly on our location, extending radially outwards and gradually recovering to match the expected average cosmic density. Additional support came from the Supernova Legacy Survey and other Type I supernova projects, which observed dimming and redshift patterns consistent with a void-like structure. Moreover, observations of galaxy flows, bulk movements of clusters in large-scale cosmic regions, also point to gravitational imbalances in our local region. If there is a void in one direction and an overdense region in the other, the differential pull causes peculiar velocities, detectable through redshift measurements. These flows provide another way to feel the gravitational contours of space, like tracing the invisible hand of mass and absence. Another intriguing method for void detection is weak gravitational lensing. By measuring how the light from distant galaxies is distorted as it passes through cosmic structures, scientists can infer the mass distribution of space. In areas with significant mass, light is bent strongly. In voids, the bending is minimal. The KBC Void has shown up as a low-lensing signal region, reinforcing the case for its existence. We also need to touch on the Sunyaev-Zeldovich (SZ) effect, particularly the kinematic SZ effect. This involves the scattering of CMB photons off of moving clusters of electrons, providing another sensitive probe of large-scale structure. Regions with excess motion or unusual density patterns show up in these analyses, and models incorporating the KBC Void show improved fits to observed data. As researchers continue to explore this fascinating region, computer simulations play a vital role. Cosmologists create enormous virtual universes governed by physical laws and filled with simulated galaxies, voids, and filaments. By tweaking parameters such as void depth, radius, and gradient, they generate theoretical predictions that can be directly compared to real observations. These simulations help validate or falsify the notion that the KBC Void can resolve cosmological discrepancies, such as the Hubble tension or anomalies in CMB and isotropies. But the deeper we go, the more questions arise. If the KBC Void is real, what caused it? Is it the result of natural evolution from quantum fluctuations in the early universe, magnified through inflation? Or does it point to new physics, perhaps a misestimation in the matter-energy content of the universe, or unknown interactions between dark matter and dark energy? Could it be the result of anisotropic inflation, regions of space expanding at different rates in the early moments of the universe? One particularly bold idea is that the KBC Void may be connected to topological defects in space-time, leftovers from phase transitions in the early universe. These defects, such as cosmic strings or domain walls, could act as attractors or repellers of matter, leading to the formation of immense voids or dense walls over billions of years. Alternatively, it's possible that the KBC Void is not a single structure at all, but a composite of overlapping smaller voids, a void complex, rather than a uniform underdensity. This would fit with the overall clumpy nature of the cosmic web and allow for a more nuanced interpretation of our local environment. Even the nomenclature surrounding the KBC Void opens up interesting debates. Should we really call it void if it contains galaxies, albeit fewer than average? Technically, a void doesn't mean absolute emptiness. It means an underdense region. But the psychological weight of the word void carries implications of utter isolation and silence. In reality, the KBC Void is not an empty abyss. It has matter, structure, and complexity. It has galaxies, intergalactic gas, dark matter filaments, and magnetic fields. But compared to the average cosmic density, it is strikingly empty, and that's what makes it so cosmologically significant. As we explore this enigmatic structure, we are forced to confront the idea that our understanding of the universe is still in its adolescence. For all the sophistication of our instruments, for all the precision of our measurements, we are still fumbling in the dark, trying to stitch together a coherent picture from fragmentary data. The KBC Void, far from being a distraction or a footnote, might be the key to rethinking some of the most fundamental ideas in cosmology. And perhaps, just perhaps, it is trying to tell us something about the deep symmetry and asymmetry of the universe we inhabit. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.